All right, hello, chemistry class. This is Coach Jeans, and what we're going to talk about in this video podcast is about mole conversion. So, hope these videos help you out, and you'll get a lot out of this. Now, once you understand what the concept of a mole is, you understand that a mole is like a dozen. But it's a lot bigger number. It's 6.02 times 10 to the 23rd of whatever. That's usually atoms, ions, or molecules. You understand that the mass of a mole is what we call the molar mass, and you find that by looking at the chemical formula and using your periodic table and finding the atomic mass, and then just adding that up and finding the molar mass of the compound. And you'd understand that the mass of a gas, or the molar mass of a gas at standard temperature and pressure, is 22.4 liters per every 1 mole. So using these concepts and using this, we can then make conversions between moles, and we can convert them over to grams, or we can convert them over to particles, or we can convert them over to liters. Now, on the screen, you see there are 3 conversions. So you want to pause the video here and copy this screen down and copy these conversion factors down. Okay, after you have paused the video and copied these down, understand that when you're talking about a mole, this blank right here represents the molar mass. So whatever chemical formula you have here, you calculate the molar mass like we've discussed, and that number goes beside the grams, and that's per 1 mole of whatever chemical it is, whatever chemical formula, whether it's H2O or CO2 or sodium phosphate or whatever it might be. All right, if you're talking about particles, now again, remember particles, that could be atoms, ions, molecules, then they're always 6.02 times 10 to the 23rd particles, atoms, ions, molecules per 1 mole of those atoms, ions, and molecules. If you're dealing with gases, assuming that it's standard temperature and pressure, that's 0 degrees Celsius and 1 atmosphere, then the volume of 1 mole of any gas, it doesn't matter what the gas is always 22.4 liters of that gas per every 1 mole. Now, when we do these calculations, we can use these conversion factors and we can flip them depending upon what needs to be canceled using what's called dimensional analysis or factor label method, or I like to call it the T-chart. So what you want to do now is you want to just pause this video and you want to copy this diagram down someplace in the back of your notebook, or if you're not using a notebook, on a separate sheet of paper, but preferably it's in the back of your composition notebook, and you'll have it handy for you to use both in this unit and the next unit, and really throughout the rest of the year if you need it. So copy the mole map in the back of your notebook to use for mole conversions. Pause the video here for a few moments and just copy this down. Okay, after copying this down, I want to go through this. On the mole map, what you'll see is right here in the middle, we have just the mole map, and it's divided into 2 halves. On the left side, we have the given side. The right side, we have the unknown. Now, in the middle here, we have what's called the mole ratio. On the left side is the moles given. Here's the moles unknown. Now, in order to go from moles given to moles unknown, we use what's called the mole ratio, and that comes from the balanced chemical equation. Now, we're going to get there a little bit later. Right now, what I want to do is concentrate over here on the left-hand side, because we're basically going to do some basic conversion from moles to liters, or moles to grams, or moles to particles, okay? So, if you're moles and you're starting right here, we like to kind of think about this as a city, then you have to travel down this road to get to mass, which is always in grams. In order to get from moles to grams, we use grams over moles, and so you calculate the molar mass. Now, if you're in moles and you try to get to particles like atoms, ions, molecules, then you're going to use Avogadro's number of things, 6.02 times 10 to the 23rd atoms, ions, molecules per 1 mole of those atoms, ions, molecules, whatever the problem is asking you. All right, if you're trying to go from moles to liters, which is volume of a gas, again, assuming standard temperature and pressure, then we know that there are 22.4 liters per 1 mole. So you can use this as conversions. Now, if you're going the opposite direction, for example, you're going liters to moles, then you do the same thing, but depending on your setup, what you're going to have to do is you're going to have to flip this, okay? So it just depends on what direction you're going. Actually, when you're going from moles to liters, this will be flipped. When you're going from liters to moles, it's simply going to be 22.4 liters. All right, so the same thing here. When you're going from mass to moles, you're going to have this flipped, okay? Grams are going to be on the bottom, so this is going to be flipped. I'm going to show you some examples. Same thing with particles. Particles to moles, okay? You're going to use this, but it's going to be flipped because particles are going to be on the bottom. So the 6.02 times 10 to the 23rd will be on the bottom, and the moles will be on the top. Now, remember this, for these types of conversions, now when we get to some different ones, the number will change a little bit. But for this type of conversion, the 1 always goes beside the mole, and then the other number, if it's grams, it's the molar mass. If it's liters, it's 22.4 liters. And if it's particles, it is 6.02 times 10 to the 23rd. That goes with the other unit. I'll show you how this is set up when we do some examples of this. So let's flip over into our notebook and let's do a few examples. All right. So we've got the paper here, and these are all, these first ones that we're going to do are all going to be one-step conversions. All right. So at the top of your paper, you want to write down one step, get that where you can see it, one-step problems. Okay. We're going to do several examples of these. And again, pause the video as needed. If I'm going too fast for you, rewind it, look at it again, whatever that you need to do. All right. So example number 1. Okay. Let's do example number 1. Let's say that we have 3.50 moles of, let's say, CO2. And I want to know, well, how many grams of CO2 is that? All right. So we're going to start this out. We're going to use what's called the T-chart method, or most people call it dimensional analysis. Factor label method is another word for it. So we're going to write down what we're starting with first, 3.50 moles CO2. And then we're going to draw the factor boxes, or I call them a T-chart because it looks like a real big fat T. Now, you can put a 1 underneath this if you want to, but you don't have to. It's kind of understood, but a lot of times I will, but sometimes I won't. So moles here is what we're converting. So we need this to cancel out. In order for this to cancel, it needs to go to the bottom down here. So automatically, we put whatever units in this top left box to the bottom right box, okay? So now we're trying to go from moles to grams. So we look at our mole chart that we just made, our mole map. We're in moles, and we're trying to go to mass, which is grams, okay? And so moles to grams, this is mass right here, okay? Should probably write that on this one. Mass is in grams. So in order to do that, what do we need? Well, we need the molar mass, all right? So we're going to put grams of CO2 on the top right there. Now we need to figure out the molar mass that goes in this blank right here, all right? Come to the main office. All right, you can see I'm still at school here today. So we're going to have carbon, we're going to have oxygen. Then we're going to get our periodic table, and we're going to look up the molar mass. So we have carbon first, and we see it's 12.01. So we get that from our periodic table. All right, and we're going to multiply that by the number that's in the formula. So it's just times 1. So that's 12.01 right there. Then we're going to go to oxygen. We look it up on the periodic table, and again, it's right here. So we see that it is 16.00. All right. Times what? Times 2, because there are 2 oxygens in the formula. So that's going to be 32.00. And so what we want to do is we want to just add all this up, all right? So what does that give us? 44.01. So that's going to go besides the mass. 44.01 is what's going to go there. So now moles on top will cancel out with moles on the bottom. So we take our calculator, and since dividing by 1 is not going to change anything, we're not going to worry about the ones. We're just going to multiply straight across the top. So 3.5 in your calculator, punch in. You need to, if you don't have a calculator, pause the video and get your calculator out. It's 3.5 times 44.0. And when we get that answer, we're going to round it off to just 2 decimal places. So we're going to put 154. You could stop there if you wanted to do significant figures. There's 3 here. So, or if you want to, just round it off to 2 decimal places. That's typically what we're going to do in class. Just kind of makes it easier and simpler. And that's going to be grams of carbon dioxide, okay? All right, so that'll be our final answer for that one. Okay, let's go to example number 2 here. All right, for example number 2, we're going to say 35.9 grams of O2. And we're going to say, well, how many moles of O2 is that? How many moles are we going to get? So we're going to start off the same way. Whatever number is given to us, that's what we start with, 35.9 grams. And I'm going to go ahead and put the O2 in there. It only takes a few seconds to write the O2, and it will help you keep things straight, especially when we get more complicated. We're going to draw our T-chart. We're going to put grams of O2 on the bottom. Why? So it cancels out. So whatever the unit is here, automatically goes down there. We don't even have to do any more analysis than that. We just put it down there exactly the way that it is. All right, we're trying to convert over to moles. So we're starting in grams and we're converting it over to moles. So we're still going to use grams over moles, but now we've got to flip this. We've got to invert it. Why? Because grams are on the bottom. So we're going to put moles on top, and the one, for these types of problems, the one always goes with the mole. Now, what's going to be the here? That's going to be the molar mass. Well, it's O2, so that's 2 oxygens. 16 times 2, okay, equals what? 32.00. All right, so we're going to write that right here because that's what goes beside the grams. All right, grams cancel out. Moles is in our top, so that's what we need. So now we're ready to use our calculator. Now this time, we have 35.9 times 1, but again, that's not going to change anything. So then we just hit divided by 32. So what I do is I just ignore the ones. 35.9 divided by 32. And that's going to equal to 1.12. Try that on your calculator. Make sure you're getting that along with me, okay? And then the unit is whatever's left over here. It's moles of O2. So that would be our final answer for example number 2. All right, let's go on to another one. Let's go example number 3 here. And let's say we have 2.2 moles of the element boron. And I want to know, well, how many atoms are in 2.2 moles of boron? So what are the number of atoms here? All right, so I started out the same way. So you'll see there's a process here. There's a method here, 2.2 moles. Whatever my problem gives me, that goes first. Draw my factor boxes, okay, my T-chart. Whatever unit is here automatically goes here. Now I'm in moles, and I'm trying to go to atoms. Well, where would atoms be? That's a particle. Atoms are particles. So now I'm going to use Avogadro's number, 6.02 times 10 to the 23rd atoms per mole, okay? So I'm going to put atoms right here of what? Boron. And I'm going to put 6.02 times 10 to the 23rd right there. Over what? Over 1 mole. Remember, the 1 goes beside the mole. The other one goes beside whatever you're trying to find. Moles will cancel out, and moles will cancel out. Now, you need a scientific calculator. So make sure you're using a scientific calculator. And you want to find the EE button on your scientific calculator. Let me grab one. So here is the typical type of TI-30 calculators that we typically use, or you may have a different calculator, but right here is where your EE button is, and it's a second function. So what you want to do is you want to hit second, and then you want to hit EE, and that EE represents times 10. So make sure you're using that on your calculator, okay? So let me cut this one on, we'll clear it out, and I'll show you how to do this problem using your calculator. What you want to do, basically, is you want to punch in your calculator 2.2, and then since it's on top, you want to hit the time symbol. You want to punch 6.02. Now, here's what you want to do. Hit that second function and then the EE button, okay? That EE means times 10. Then you're going to put 23 for the power of 10 and then hit equals. All right, so on the calculator, here's how it goes. You're going to hit 2.2 times 6.02, second function EE to the 23rd, okay? And you're going to hit equals right there, all right? And when you do, that's what you're going to get on a calculator, 1.3244. Then you'll see it says times 10 to the 24th. Some calculators are a little different, but most of them work very similar to that. So we're going to round it off to 1.32. We'll just go 2 decimal places times 10 to the 24th power. Make sure you have the times 10. If your calculator comes up with E something, that E stands for times 10. So write it with the times 10 symbol. That's the way it's written. And then what is going to be the final unit? Atoms of boron. Okay? All right, let's do one more problem before we go here. Let's do example number 4. All right. And we'll get this one done. And this time we're going to do liters. We're going to go 45.5 liters of NO2. And we're going to try to figure out how many moles of NO2 that represents. All right. Now, again, this is at STP, so we need to assume that it's standard temperature and pressure. That means 0 degrees Celsius and 1 atmosphere, or 101.3 kilopascals. All right, so we always start out with what's given to us, 45.5 liters of what? NO2. Make sure you write the NO2 with it. Now, liters, NO2 is going to go down here. We're going to convert it over to moles. So we consult our mole map again. And so this time we're starting out with liters, and we're trying to go to moles. So what are we going to use? 22.4 liters per 1 mole. Well, where does the 22.4 go? It goes with the liters. So we put it at the bottom, 22.4, and the 1 always goes with the moles. Notice the 1, on these types of problems, the 1 always goes with the moles. Liters NO2 cancels with liters NO2. And so now we take our calculator, 45.5 divided by 22.4. Since 22.4 is on the bottom, we just hit divided by. So 45.5 divided by 22.4, and we get 2.03 what? Moles of NO2. And so that would be our final answer for that problem. This one was our final answer here. So I hope this video helps you, and I'll see you in chemistry class. We'll work a lot more examples, give you a lot of time to practice, and you can ask any questions that you might have.